In this chapter, we will reference previously discussed indexes, but focus more on how they work and the various types of indexes. Remember, an index is used instead of going through all data. It is for reference purposes. Using indexes are helpful with databases for referencing and more. Here, notice the secondary access paths. This is what I am talking about when I use the term references. Here, we describe our single-level ordered index. Remember from our earlier database query, results are not necessarily ordered. Our index can do the ordering for us. Here, we define two common single-level ordered indexes in a clustering index and a secondary index. Here, we define a primary index. Notice the differences from previously touched on indexes. Here is a visual example of a primary index. There are issues associated with adding or deleting records with a primary index. So here are two common solutions. Here are clustering indexes further described. Here is a visual example of a clustering index. Here are secondary indexes further described. Secondary versus primary. Here is a visual example of a secondary index. Do you notice the clear differences between what these three indexes look like and do? Here is a summary of the properties of our discussed index types. Notice how the dense indexes were visually more involved. In addition to single level, there are multi-level indexes, with their level defined as first, second, and third level as appropriate. Here is a visual of a two-level primary index. B trees and B plus trees may have been seen in a data structures course in programming. Here is a visual of a data tree. Notice the variance of nodes. You may recall from data structures, binary search trees, where they could be unbalanced or balanced. Well, B trees are balanced. We can use a search tree for more accurate query results, using paging, where the operating system brings data in depending on your needs. We can also search tree to update a database by inserting or deleting data. B trees are used based on these properties associated with them. A B tree, again, is a balanced tree. It produces a linear search of the values through the value fields. Here is a visual representation of how a B tree looks. B plus trees are enhanced versions of B trees with internal nodes and additional data pointers. A B tree which contains all values on leaf nodes and links all nodes together is a B plus tree. Here is a visual representation of how a B plus tree looks. Notice the visual is not as complex as the B tree may have looked. Here is the SQL code associated with a search using a B+ tree. Remember, we can use database programming. We can index of multiple keys using a variety of methods. Here is a general representation of a multiple key index. Notice the array and matrix. Hash indexing is one of the most common multiple key index used. Here is a visual representation of a hash index. We use bitmap indexes when we have a lot of data to retrieve. A bitmap is often viewed as an image. You can also set an index based on functions. In this example, we are only allowing last names to be submitted as capitalized or uppercased. There may be some issues which cause us to avoid using indexes despite their power. We can create an index in SQL as we need them. Like in programming, we may want to create an index array of strings. We can, but we may be limited in how much data we can store. Our indexes may need to be fine-tuned to give us the exact results we are looking for. Think of using access. If we put the wrong criteria, we get the wrong results. There are other issues related to storage. Some are basic constraints, others are associated with view and fit. Our database needs to be created based on the relationships within the database and the data needed. Hence, why we create our ER diagrams before our database. We need to consider the following when deciding if an index is needed or not and which one fits our needs. You should now have a firmer grasp on indexing within databases.